Hello and welcome to Astronomy Daily, your daily guide to the universe and everything in it. I'm Anna.
And I'm Avery. It's Tuesday, the 6th of May, 2026, and we are coming at you with 6 incredible stories today. From a robotic telescope that just read the geology of a world 50 light years away, to a meteor shower you can watch live online right now.
That's right. And we have a stunning mix of planetary science, exoplanet discovery, cosmological simulation, and some very welcome skywatching news for our Southern Hemisphere listeners.
Let's get straight into it. Story 1 is genuinely historic.
For years, when astronomers pointed the James Webb Space Telescope at a distant rocky world, they were really studying its atmosphere, the thin shell of gas around a planet. Today, we're talking about something different. Something that has never been done before.
That's right. Astronomers have now used JWST to directly analyze the actual surface of a planet beyond our solar system. Not its atmosphere, its surface, the rock itself. And what they found is remarkable.
The planet in question is called LHS 3844b. It's a so-called super-Earth, about 30% larger than our own planet, and it sits roughly 48.5 light-years away, orbiting a small, cool red dwarf star.
Now, this planet is an extreme situation. It orbits its star so closely that it completes a full year in just 11 hours. 11 hours, Anna. That's your entire working day and then some.
And because of that extreme proximity, it's tidally locked, meaning one face permanently points toward the star, baking in intense heat, while the other side sits in permanent darkness. The day side reaches temperatures of around 725 degrees Celsius. That is hot enough to melt lead with room to spare.
The research team led by Laura Kreidberg at the Max Planck Institute for Astronomy in Germany used JWST's mid-infrared instrument, known as MIRI, to measure the thermal emission radiating directly from the planet's blazing hot day side. They observed 3 secondary eclipses, moments when the planet slipped behind its star, and used those measurements to build a picture of what the surface is made of.
And the result? Dr. Kreidberg described it directly. We see a dark, hot, barren rock devoid of any atmosphere. The surface appears to be composed of dark, low silica material, probably basalt or other olivine-rich rock. Think volcanic plains, like those you'd find on the moon or on Mercury.
Importantly, the team was able to rule out a number of things. There's no Earth-like silica-rich crust, the kind that forms through water-driven geological processes and plate tectonics. There's no evidence of accumulated volcanic gases, no carbon dioxide, no sulfur dioxide. This is a geologically quiet, airless, ancient world.
And while that might sound a bit bleak, the significance here is huge. The published paper in Nature Astronomy calls this the next step in unveiling the nature of distant planets. We're no longer just detecting exoplanets or guessing at their atmospheres. We're starting to read their geology.
Think about what that means for the future. With more observations like this, we'll be able to build up a geological census of rocky worlds across the galaxy. That knowledge feeds directly into our understanding of which worlds might be capable of supporting life, and which are simply very impressive, very hot pieces of rock.
A dark, hot, barren rock. But a dark, hot, barren rock that just made scientific history.
Sticking with the theme of worlds that are frankly hostile to life, let's talk about Io.
Jupiter's extraordinary moon, the most volcanically active body in the entire solar system. A world being continuously kneaded by the gravitational tug-of-war between Jupiter and its larger sibling moons, Ganymede and Europa.
Io has over 400 volcanic features called paterae, essentially giant depressions filled with lava lakes. Scientists have been measuring the heat output of these features for decades, and a new study released just yesterday suggests we've been getting it dramatically wrong.
The paper, now available as a preprint on arXiv, uses data from Juno's infrared instrument, the GIRAM, to look at Io's paterae in a completely new way. And it turns out previous measurements were only seeing part of the picture.
For a long time, scientists measured Io's volcanic heat output using what's called the M-band of infrared. And the M-band is excellent at picking up the really hot bright spots at the active edges of lava lakes, where fresh, uncooled magma is churning. What it misses is the vast, cooler, older crust that forms across the rest of the lava lake surface.
And that crust, it turns out, is enormous. It's much, much more massive than those hot peripheral rings. So while it's cooler in temperature, its sheer scale means it contributes a staggering amount of total thermal output. The team used JWST's updated data, which can detect those lower temperatures, to build a revised picture.
For one well-studied Patera alone, known simply as P63, the old estimate was around 7 gigawatts of thermal output. Some models put it at 20. The new JWST data? 80 gigawatts from a single lava lake.
To put that in perspective, the entire output of the UK's electricity grid is around 40 gigawatts. One volcanic depression on Io is putting out double that.
And that's just one of the 400 Paterae. The study only looked at 32 of them. The implications for Io's total heat budget are significant. We may have been underestimating this moon's thermal fury by an order of magnitude.
And the study also found something intriguing about the crust itself. Using thermal cooling models, the team estimated that a crust at 200 Kelvin would be roughly 13 years old, meaning these lakes resurface on timescales of about a decade. So the geology of Io is incredibly dynamic, constantly renewing itself.
Io never stops surprising us, and now, thanks to Juno, we're starting to truly understand just how powerful this extraordinary little moon is.
Now we're going to zoom out, way, way out, from one single moon to, well, the entire universe.
An international team of astrophysicists, led by researchers at Durham University in the UK and Leiden University in the Netherlands, has just released one of the largest cosmological datasets ever assembled. We're talking about 2.5 petabytes of data.
2.5 petabytes. That is equivalent to roughly 500,000 high-definition movies, all now freely available to researchers anywhere in the world.
This is the FLAMINGO project, a suite of large-scale computer simulations that model how matter has evolved across the universe right from the Big Bang through to the present day. The simulations were run on the Cosma 8 supercomputer at Durham, which is part of the DRAC National High Performance Computing Facility in the UK.
And what makes FLAMINGO special is its scope. Many detailed simulations focus on small regions of space. You get great detail on individual galaxy formation, but you can't see the big picture. Other simulations capture vast cosmic volumes, but lose resolution at the small scale. FLAMINGO does both.
Its simulations stretch across billions of light years, allowing researchers to study rare, massive structures like galaxy clusters while still capturing the physics of individual galaxy formation. The cosmic web, that vast network of filaments and nodes along which galaxies are distributed, is reproduced across these volumes in extraordinary detail.
The data includes 22 full hydrodynamical simulations, galaxy and halo catalogs, all-sky maps, and particle data. Because the dataset is so vast, the FLAMINGO team also built a custom web-based system, so researchers can access just the data they need without having to download the entire archive.
Matu Schaller of Leiden University summed up the ambition well. Open access to datasets of this scale can significantly accelerate scientific progress. Since FLAMINGO simulations were first introduced in 2023, they've already been used in dozens of studies. Now the full dataset is public. The scientific community can do so much more.
This is open science at its most ambitious. Virtual universes freely given to the world.
And hopefully, the world will receive it in the spirit it is given.
Now, before we move on to our next story, I'd like to quickly remind you of our sponsor, NordVPN. As I keep saying, when you're ready to secure your online life, make sure you get NordVPN. It's the one we use and swear by. And we can help you save a heap of money, along with a 30-day money-back guarantee, which means there's nothing to lose. When you're ready to check it out, make sure you use our special link, which you'll find in the show notes.
From the very large to the very precise,
Our next story is about a clever new technique that's unlocking a whole new population of planets that we've been struggling to find.
This one has a lovely Australian connection, which we always enjoy. The study was led by Margot Thornton, a doctoral candidate at UNSW, the University of New South Wales in Sydney, and it tackles a real challenge in exoplanet science.
So here's the problem. NASA's TESS satellite finds planets by detecting tiny dips in starlight as a planet passes in front of its star. It's brilliant, and it's found hundreds of confirmed planets. But there's a class of systems it really struggles with: binary stars.
Binary stars are pairs of stars in orbit around each other, and they're very common. A huge fraction of stars in our galaxy have a companion. The complication is that when you have two stars doing their own thing, it becomes very hard to tease out the much smaller signal of a planet passing in front of one of them.
But this new approach uses a different approach entirely. Instead of looking for the planet's shadow, it looks for the planet's gravitational fingerprint. As a planet orbits in a binary system, its gravity gently tugs on the stars, and that changes the precise timing of when the two stars eclipse each other.
It's a beautiful idea. You're not watching the planet at all. You're watching the stars dance and noticing when something is slightly out of step.
And it works. The team applied this eclipse timing technique to test data and uncovered more than 25 new exoplanet candidates orbiting in binary star systems where traditional transit detection methods simply couldn't find them.
Before this study, only 18 such circumbinary planets had ever been confirmed across all telescopes combined. 16 from NASA's retired Kepler mission, plus 2 found by TESS itself. This new method has the potential to dramatically expand that number.
It's a reminder that the way we look for things matters as much as what we're looking for. Great work from the UNSW team, showing that Australia is very much at the frontier of exoplanet discovery.
Our penultimate story takes us to the outer solar system, to those mysterious, underexplored giants, Uranus and Neptune.
We often call them the ice giants, but that's a bit of a misnomer. Their interiors are not cold at all. They're subjected to temperatures in thousands of degrees and pressures millions of times greater than anything at Earth's sea level. It's an environment we simply cannot recreate in a lab.
And because of that, the physics of what happens to materials under those conditions has long been the subject of theoretical modeling. Now, a new paper published in Nature Communications from researchers at the Carnegie Institution has added a striking new entry to that catalog.
They've identified a previously unrecognized state of matter that may exist in these extreme environments, a phase they call quasi-one-dimensional superionic. It's a mouthful, so let's break that down.
Superionic materials are already fascinating. In a normal solid, both the ions and electrons are locked in place. In a normal liquid, both flow freely. A superionic state is something in between. The ion lattice is solid, but some particles flow through it like a liquid. We actually believe a superionic phase exists deep inside Uranus and Neptune already. But this new phase is different.
The quasi-one-dimensional part refers to the fact that in this newly identified phase, the flowing particles don't move freely in all directions. They're constrained to flow along narrow, one-dimensional channels within the material structure. It's like water moving through a network of pipes rather than flooding a room.
This is significant because the behavior of materials in ice giant interiors governs everything from their magnetic field generation to their heat flow to their atmospheric dynamics. If we've been missing an entire phase of matter that exists in these conditions, our models of how Uranus and Neptune actually work may need revision.
With new missions to the ice giants being seriously discussed by both NASA and ESA for the coming decades, this kind of foundational physics work is exactly what's needed to ensure we know what questions to ask when we get there.
A new state of matter, hidden inside two worlds just a few billion kilometers away. Sometimes the most exotic physics doesn't require going to another galaxy, just the outer edge of our own solar system.
And finally, something you can do something about tonight, or more precisely, in the pre-dawn hours of tomorrow morning.
The Eta Aquarid meteor shower is at its peak right now, and for our Southern Hemisphere listeners, particularly our Australian and New Zealand friends, this is one of the best meteor events of the year.
The Eta Aquarids are the debris of Halley's Comet, the legendary comet that last swept through the inner solar system in 1986 and won't return until 2061. Every year, in early May, Earth plows through the trail of dust and rock particles Halley has left behind across its 76-year orbit. And those particles burn up in our upper atmosphere as spectacular shooting stars.
What makes the Eta Aquarids special for the Southern Hemisphere is geometry. The radiant, the point in the sky the meteors appear to stream from in the constellation Aquarius, rises high in the sky before dawn. From Australia and New Zealand, it reaches a really favorable altitude, meaning you can expect to see up to 50 meteors per hour under ideal conditions.
There is a caveat this year. A waning gibbous moon is hanging around in the sky, and it will wash out some of the fainter meteors. But the brighter ones, the proper fireballs, should punch through just fine. Your best window is in the hours before dawn, away from the moon, lying back on a blanket and looking up.
And if clouds are in the way, or you're deep in the city, or you simply can't face a 4 a.m. alarm, there's good news. There are free live streams of the shower available online. One particularly impressive option comes from the ALMA Observatory in Chile's Atacama Desert, one of the driest, clearest places on Earth, and one of the premier sites in world astronomy. You'll find links in our show notes.
So whether you're watching from a dark paddock under the Milky Way or from your lounge with a coffee at sunrise, you can join millions of people tonight in witnessing the cosmic legacy of Halley's Comet.
Shooting stars. Every single one a tiny piece of one of the most famous objects in the history of human sky watching. That never gets old.
And that's a wrap on today's Astronomy Daily. We've read the geology of an alien world, we've discovered Io is even more powerful than we thought, we've opened 2.5 petabytes of virtual universe to the world. We've found new planets around binary stars, we've discovered new states of matter inside ice giants, and we've told you exactly where to watch a meteor shower tonight.
Not a bad day's work for a Tuesday. If you enjoyed today's show, please subscribe, leave a review, and share us with a friend who loves space as much as we do. You can find us at astronomydaily.io and on socials at AstroDailyPod.
We're part of the Bytes.com podcast network. Until tomorrow, keep looking up.
This is Anna.
And Avery.
Clear skies, everyone.